Welcome to the classroom. Today we're talking about breaking rocks with the point load test. The point load test is an index test. We can get the load index strength and we normalize it to an equivalent diameter of 50 millimeters. We take the peak load at failure, and this is the point load testing device. We have two conical points, and this apparatus was first designed in its more or less the equivalent form and the standard method of testing by Franklin in 1972. And Brock also did some advanced testing, but they basically developed this test apparatus and it stayed the same. It's very popular in use out in the field. We can take this out to the field. It's not too heavy, and we can actually use it even on irregular samples or even our core specimens, okay, that we would get while we're drilling. So it's a great test to do in the field. The core comes in off the drill rig, and you automatically can do some tests right there in the field. So it's a great opportunity to get a very good first estimate of the strength values. But these are all empirical relationships, so it's not really a direct measurement of the tensile strength. But the sample is failing in tension. So you can actually see the sample here. I've tested prior, and you can see some breakage. That's where the point has actually gone in and caused some compression, but the sample can expand and actually breaks in tension. Okay, here is another example. You can see the crushing at where the points went in. Goes down into the sample a little bit, but in the center we're basically failing the sample in tension. All right, but it's an index test. It's an indirect test. It's not a direct measurement of tension. That would be where we actually pull it apart, so the stresses are acting in the direction of failure, or perpendicular to the failure in tension. If we're going to test along the core axis, the sample length needs to be twice the diameter, all right, or more. So this is a good size sample. It's about 63 millimeter diameter, and we can measure the length with the caliper, and it's 124 mils. So that means we have twice the length as the diameter, all right? And we can also test parallel to the core axis, okay, down in this direction, and in that case, the width of the sample has to be about 0.3 of the diameter, so you can test thinner discs. So this is a good way to use up small pieces of our core and get an estimate of the strength. And we're going to do some testing now to compare testing parallel to bedding. So this core was drilled vertically and we have horizontal beds. So we're going to test this way, parallel to bedding, and in this direction, perpendicular to bedding. And let's see which one is stronger. I've got my first sample here. We're going to load parallel to bedding, and I'll get it set in the middle, and away we go. Let's see how strong it is. A half a kilonewton. Let's do our next test, sample number 2. Oh, a little more strong that time. But actually in the measurement, 0.62 kilonewtons, and the last one was 0.58. So it's only a little bit stronger in terms of the actual pressure. All right, now we're going to load these perpendicular to bedding, and you can see we've got a safety shield in place just in case it's a little bit stronger. Let's check it out. All right, we should be good to go. Here we're rolling. Oh boy, it's going to be exciting. Whoa. 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 Good thing we had the safety shield. All right, let's test one more just to be sure. I'm going to write that down. That was explosive. It's pretty common actually to get chipping and partial breaks and stuff in the point load test. So you need to do lots of those tests in order to get a good range of values and eliminate those that are invalid. There we are. That was the strongest, least explosive, but it's still strong. All right, but we're chipping off pieces from the top. So we have actually crushed the bits of the top. We haven't driven the crack all the way through. All right, so we have just seen a lot of tests done on our limestone samples here. We saw tests parallel to bedding and tests perpendicular to bedding. And so we noticed that it's a lot easier to drive cracks parallel to bedding. And that's because if we look closely at the bedding, there are lots of actual flaws there already. Okay, there's lots of flaws parallel to the beds, and they're all oriented in that direction. We apply the force actually around all these flaws. We can grow other microcracks. You can't see them, but they're starting to form prior to failure, and then they line up and you fail. But when we are loading perpendicular to the bedding plane, those microcracks are this way, so the cracks can grow that way, and then they have to jump and they move around, so the fracture pathway is a little bit more irregular. Just like groundwater, if the pathway for flow is a lot more complicated, it takes longer to flow through. So same with crack growth. If there's a lot more obstacles in growing the crack, then it takes longer for the cracks to grow, and therefore we can apply higher load. So that is a very interesting concept as a strong engineering link, because when we make a tunnel underground, the orientation of the bedding, whether it's horizontal or inclined beds or foliation planes, we need to account for what we call anisotropic strength. The strength in this direction is weaker than this direction. We call it anisotropic strength, and it's a very important factor in designing our underground excavations. So that's the engineering link.